So in the previous session, we were looking at the BPSK modulation technique, and in the same, we have already considered the block diagram and also the power spectral density of the BPSK. Right? Now, let us try to calculate, uh, say, the coordinate of message points. Right? If I want to measure the coordinate, so that I can draw the constellation diagram. So first we have to calculate the required coordinates. Right? The coordinates of message points. So this is how we calculate. So S11 is equal to integral 0 to TB, like we calculated in the ASK case. So first you have a message signal you receive, that is S1 of T, into the phi, right, dt. So when S1 is sent, you will receive this as root EB. At the same time, right, whenever you send the second signal, that is S2, this will be equal to integral 0 to TB. This is the second message signal, that is S2 of T, into the phi 1 dt. So that means you are going to receive minus of root E. Right? That means so the constellation diagram is going to look something like this. We have the axis. This is the line corresponding to our basis function, that is phi 1. Right? Let us say this is 0. Somewhere here, I will represent that as the first point, that is the root of EB. Say this is S1. Similarly, on the other side, I'm going to get the S2, the symbol corresponding to 0, that will be minus of root EB. Right? Now, it's very clear that the decision boundary has to be the 0 point itself. Correct? So this will be the decision boundary. Decision boundary. So that means, right, let's mark the regions now corresponding to the reception of the first point, that is symbol equal to 1, right? It has to be marked over here, anywhere starting from 0 to infinity. At the same time, if you want to mark the region that should be responsible for identifying the symbol equal to the symbol 0, right? That should be right over here. Right? Anyway, the point corresponding to any point that is lies in the region, we mark it as region Z2. So let's call this is region Z1, region Z2 corresponding to S2. So decision boundary is at the center. So this is how we try to write the constellation diagram. Okay, now how do you select the point, right? How do you try to decode the point, right? So we can call it as a decision tree. Right. So choose the signal, that is S1 of T, or maybe the binary symbol 1, if the received point X1 falls in Z1. Right. So let's try to write that here. So if the received point X1 in Z1, this means you decode that as symbol 1. Okay. At the same time, if the received point, that is X1 in Z2, you will call that as, so if that is the case, then we are going to decode that as the symbol 0. Right? So that's a very simple rule for the detection. All right. So using this, now we'll go for the demodulation or the detection of the BPSK. Detection of BPSK. Right. So let's try to write the block diagram. So let's say we receive the signal that is denoted as x of t, which is nothing but the BPSK signal received. That signal, since this is going to be the coherent detection, we definitely expect that we know that what is the value of the phi 1 or the carrier used. It's also called as the basis function. All right. So let us try to multiply over here with the phi 1 of t. Right. So I multiply with the phi 1 of t. So this result is going to be then passed through an integrator. So here we perform integration of, so maybe 0 to some time duration. Let's try to write that as t, the received function into dt. Okay, altogether the product modulator and this integrator is called as the correlator, right? We used the same term yesterday, so this becomes easy. Okay, so then we have a sampler circuit. So sampler circuit will perform the sampling in the following fashion. So at this point, we have some value coming up. So the same thing we would like to do a sampling. So how do you sample? You move this. You make the point to touch this at every t equal to t. We call it as a sampler circuit. Right. So once you perform the sampling operation, you get a single value for every sampling duration that is equal to t. So we try to denote that sample which comes at the as the output of the sampler at every time you sample it. We call it as a x1. Right. So now we pass this through a decision making circuit. So just now we discussed that, right? What is the reason on the constellation diagram? You should get the x1 so that you can make a decision like either 0 has been sent or 1 has been sent, correct? So we know that. So that value will be passing it as a threshold value. Okay, so this is, say, we will call it as V threshold. So you can see that from the constellation diagram, it is very clear that the threshold value is now. So what is the threshold? The decision boundary. You can see that the decision boundary is at 0, right? So that's what will be used as a V threshold. So VTH is equal to 0, right? So now this VTH we are going to use to make the decision to get the binary wave. So this is the decision that comes out. Right? So that will be, so this is how you decide. So this value can be defined in this way, right? The output is equal to, right, 1 if, what is the condition? The x1 is greater than V threshold. That is 0. So 0 if x1 is lesser than V threshold. Okay, so that's how we try to make a decision. All right, so this is the way to perform the decision process of this. So overall, you can see that at the end, you will get the binary 1 or 0 that was sent initial. All right, so that's the detection process. So now we'll directly move to the probability of error. That's also equally important. Right? So let's try to calculate the probability of error. Right. Now, let us say we received the signal and the received signal is denoted by x of t. Right. Now, we have, let us say we send the 0, right? Initially, we send 0 as our signal. So when you send a 0, what should be the received signal? We'll write. Okay. So the received signal, that is normally denoted as x of t, right? In the presence of the AWGN, right? It's actually additive white Gaussian noise. AWGN means that, right? How do you denote that? That is W of t. We used it yesterday, right? When, let us say, symbol 0 was sent. When, I'm saying that when 0 was sent from the transmitter. So how do you denote that? That means the x of t is equal to, right, out of the two different message signals, right, you can send one for 0, one for 1. I think we denoted s2 of t for 0, correct? So what you are sending now is s2 of t. With that, the channel adds a noise component denoted by w, correct? So 0 less than or equal to t less than or equal to t. Hope this is fine. Right now you see, this is what has been received as a BPSK signal. So come back to this. So that's the x of t which is here. This x of t passes through the correlator. So correlator is integration and this multiplication, sorry, multiplication first, multiplication with phi of t and then integrating. So all together, right, this will be the correlator, right? So that then right, this implies the correlated output at every t is equal to tb. This can be calculated like this. So let me call that, that is the symbol. We denote that as x1, correct? X1 is after sampling, but anyway, we can write it here now. So that is integral 0 to tb. Tb is my duration. Whatever you received, so far it's very clear that what we received is x of t, correct? So this has to be integration 0 to tb x of t, right? X of t is received into, anyway, I'm going to multiply with the phi 1 of t into dt. So that's the output of the correlator at point t is equal to t, right? But you see, what is x of t? Definitely we can substitute for x of t. So anyway, this is x of t into phi 1 of t dt. I will substitute. So that is equal to 0 to tb. X of t can be replaced as s2 of t plus a noise, that is w of t, right, into the phi of t, phi 1 of t dt. Okay, so that means you can actually write this, right? So s2 of t gets multiplied with phi 1. So I can split the integral 0 to t. This is, there is s2 of t into phi 1 of t dt plus integral 0 to tb, 0 to tb, the noise component, that is w of t into phi 1 of t. So noise also gets multiplied with this part, okay, w of t into phi 1 of t dt. So recall the previous step. After the integration, I am expecting a constant as the answer. Correct? So that means as a result of this integration, you should get the constant denoted like this. Okay, let me write that once again. So this is phi 1 of t dt. So the constants we can write it as, this is on the left hand side, I have x1 is equal to, what is this? This is s21, right? Plus the w. So this is equation number 2. So we know that what is S21? S21 is already calculated. If you remember, S21 is already calculated. So I think we have that already with us. That is S21 plus W. Okay. All right. So let me call that as equation number 2. Also already written, right? Just make a correction. So right. What is S21? Just we have calculated that part. So let's quickly go back and check. What is the value of S21? Right? So S11 is root EB, S21 is minus root EB. Right? So anyway, I can directly substitute and then let's call that as an equation number with an equation number. Right? So let me just use this. This is what is not required. So I'll write that is equal to, this is minus of root EB plus W1. Now you call this as equation number 2. Right. Now we know the specifications, right? What is W1? Where W1 is equal to sample value of the random variable W1. Sample of the random variable denoted by capital W1, right? Which has, it's a Gaussian, which is a Gaussian RV, random variable, with what is a mean? Zero mean, and the variance equal to n naught by 2. N naught is the total power. Okay, so also I can say that the x1, because of w1 being Gaussian random variable, the capital X1 is also going to be the random variable, but I'm going to write about the small x. So this implies what should be the small x? Therefore, the small x will be a sample it's a sample of uh, the random variable, that is capital X1. Okay, now, so as usual, we will calculate the, what's the first step? If you remember, calculate the mean, right? This implies the expected value E of X1 should be equal to the expected value of minus root EB plus W1. So by default, this has to be expected value of minus of root EB. So there is a minus root EB and it is the expected value of the W1, right? We have two components over there inside this bracket. So that means we are going to calculate the expected value of both the both of them separately. Then we are going to club them to get the actual answer, right? So that's what we did earlier. Same thing we are going to follow. So, right, this is the expected value of minus of root EB. That's the first part, plus the expected value of say W1. Okay, so what is the expected value of minus root EB? It's a constant, so it remains same. It's minus root EB, and the mean of the noise is 0. That's why this value becomes equal to minus root EB. You can denote this as mu as well. Normally, that's the way. Right? Also, we calculate the variance of this. This means the variance of x1. How do you calculate? That is equal to this is equal to the variance of minus of root EB plus W. So normally you split this, therefore this is equal to variance of minus of root EB plus the variance of W. So that means this has to be equal to, what is the variance of the constant value, that is minus root EB? It's a 0 because it's a constant, it's not going to vary. So if it is a constant, it's not going to vary, right? So the variance of that constant becomes equal to 0. So this is variance of W1, that is equal to the first part. I can write this is 0 plus this is n naught by 2, isn't it? So the total answer becomes this is equal to n naught by 2. So you denote this as the sigma square. That's the standard notation for variance. Okay, so since we calculated for transmitting 0 now, let us try to write the conditional probability density function, right? So therefore, so just try to recall. Yesterday we did this very slowly, but I'm going faster. Okay, so therefore the PDF probability density function of say x1, given that, so I'm trying to say that it's a given condition. Okay, so given, so I can say that given that, so what's the condition? Symbol 0 is sent. Okay, so given that symbol 0 was sent, right? So if the symbol 0 was sent, how do you write the conditional probability? What is the equation for the conditional PDF? Conditional PDF is nothing, right? I have to write the fx1 of the function, correct? So how do you write that? This is equal to okay, let's write in this way. So this is equal to f, given that the symbol 0 was sent, equal to, say this is the notation, fx1 of small x1, it's a sample, given that 0 was sent, equal to 1 divided by root of, right? I need to write 2 pi sigma square into exponential of, remember this function, every time you are going to substitute this itself, right? Minus of x1 minus its mean whole square divided by 2 times sigma square. This is the function, right? So I have to substitute to this function always, divided by 2 sigma square. So substitute this always. So that means, so there is a sigma square. So there is a square. Now that means this is equal to, so substitution will give you this 1 divided by so this is 1 divided by 2 pi. What is sigma square? Sigma square is n naught by 2. So the 2 and 2 will get cancelled. So I can directly write this as 1 divided by under root. There is a pi and n naught. So I get the pi and I get the n naught, isn't it? So let me try to write in that. So this is 1 divided by root of pi into n naught. Similarly, I can also write the exponential function in the same way. Pi n naught into, this is exp of minus of x1 minus, what is mu? Mean is equal to minus root ep, right? So this is plus, the minus becomes plus, minus of minus is plus root of ep, okay, whole square divided by 2 times n naught by 2. Once again, you are left with the n naught. Okay, fine. So we call this by another equation, I think equation number 3. Equation number 3. Once you have f x1 of x1 given that 0 was sent, directly you can calculate the probability of error for 0. This implies what you are calculating, right? I'm trying to calculate the probability of error, right? So when 0 was sent, you sent 0. What is the condition for obtaining the symbol in error? What is the condition? Let's just go back to the, yeah, I think you can answer after looking at the decision problem. So you send a 0, okay, that means in region 2 you send, but if you receive the symbol in region 1, that is an error, right? So what is the condition for error? You send a symbol 0, right? When you sent 0, when 0 was sent, I can write the, okay, so when you send this, I can say that error occurs if the received symbol, because your threshold is 0, right? So you always compare with 0 if the x1 is greater than 0, right? Always you compare the same thing, right? If x1 is greater than 0, that means this is an error. So how do you write that? That is probability of error when 0 was sent is equal to the probability that the x1 is going to be greater than 0, given that, right? Right, I can write it as the symbol 0 was sent. That's a condition, right? When 0 was sent and even after that you receive the symbol in the region of 1, that's an error. Okay, very straightforward concept. So let's try to write it in the equation format like this. So when you have x1, probability of error for 0 is equal to probability of the x1 becoming greater than 0. Okay, this is x1 greater than 0. Given that, I can write like this, given that symbol 0 was sent. You sent 0, but you receive something which is right, which is supposed to be received when you have sent 1. Okay, so that means, how do you write this? So if you remember, right, if I want the probability, I should integrate the PDF. So integrate the PDF in what region? It is 0 to infinity, because x1 greater than 0 means it is either 0 or any value between infinity. So integrate the PDF we had written just now. So that is equal to fx1 of small letter x1 given that 0, right, into dx1. So substitute that. Just now we have written an equation for that. So there is 1 divided by root of pi n naught, that is outside the integration, 0 to infinity. So when I try to integrate it from 0 to infinity, right, the part containing x1 will be written inside the integral. Okay, so that part will be the exponential function which we had seen, right, in the previous equation. So let's write that. Only that part we'll write inside the integral. Okay, so that is equal to integral, so 0 to infinity, right, exponential exp of right? Minus of x1 plus root eb the whole square divided by n into dx1. All right, so the standard method to do the integration is put a value, that is u is equal to x plus root eb divided by root of n naught. You know the reason why we are taking root n naught, because the whole thing becomes a square, right? So what happens now? That means if at all I want to write the dx1, right, dx1 will be equal to n naught goes to the other side. So this equation will be always written like root of n naught times root n naught times this is du, right? So this implies when I need to substitute the same thing back. So this is equal to, on the left hand side I still have probability of error when 0 was sent. This is equal to also I need to substitute the limit, correct? So let's calculate the limit before we do this. So when you see when the x1 equal to 0, what happens to the u value? The lowest limit will be root of eb by n, right? At the same time, when the x1 becomes equal to infinity, right, it is infinity plus root eb by n naught, so u also becomes infinity. So that's the change, right? That's the change in the limit which is going to take place now. Okay, so that means let's try to substitute this back in the equation. That is equal to, so I'm trying to write PE of 0, that is equal to 1 divided by, right, root of pi into n naught integral. So lower limit changes, that is equal to root of EB by n naught to infinity. Change the function simply becomes exponential of minus u square, right, into du. But du, it's not simply du. I have a du getting multiplied by n naught, du into root n naught. So this root n naught cancels with this root n naught, and I'm going to rewrite this equation as well. So that is equal to 1 divided by root pi integral root of, that is eb by n naught to infinity. This is exponential of minus u square du, right? So this is again a very standard error function, right? So the error function is nothing but this is half RFC of root of EB by N naught. So that's what you get for the probability of error when 0 was sent. Okay, I think we can call this is equation number 4. Right, very similar to this. Now I need to do the calculation for the calculation will be for transmitted symbol being 1. Okay, so we'll write therefore similarly if the symbol 1 was sent, right, then the received signal, what is the received signal denoted by x of t, correct? So how do you write this x of t now? It is s1 of t sent symbol plus a noise denoted by w, right? So when I say that I'm going to receive this, right, what should be the correlator output? Therefore, the correlator output, that is denoted as say x1, should be equal to, right, integral 0 to tb, the received signal, that is x of t, you multiply that with the phi 1 of t. So x of t is equation number 5 now, and I need to multiply that with the phi 1 of t dt. Substitute for x of t. So this implies the x1 is equal to integral 0 to tb, right? X of t is nothing but now it is s1 of t plus w of t into phi 1 of t dt, right? So that means it is integral 0 to tb. We'll split this. So there is s1 of t into phi 1 of t dt plus integral 0 to tb. This is the noise w1 of t into phi 1 of t dt. So what is this? S1 into phi 1 integral. We already have noted down, that is denoted as S11 plus we call it as a W1. Okay, so that is equal to what is S11, right? S11 is root EB. That's the symbol, the coordinate which we have marked for S11 on the constellation diagram. Okay, so this is root of EB. So plus we can write W. So call this is equation number 6. Right. Once you have the x1, I can calculate the mean and variance. So this implies, in this case, that is when symbol 1 was sent, the mean. So I can write mu is equal to, this is expectation of x1, that is equal to the expected value of root EB plus W1. So again, you split this and you write it as expected value of root EB plus the expected value of W1. So what is this answer? This is equal to root EB, correct? So this will be, let me correct. This is equal to root of EB. All right. So that's the root EB value. That's a mean. This implies, let's calculate the variance. Variance sigma square is equal to, this is nothing but the variance of x1. So this has to be equal to the variance of the root of EB plus W1. So variance of root EB will be 0 plus variance of W1 will be n naught by 2. So the answer, so previous one was mu. Now we are calculating the sigma square, and this sigma square should be equal to n naught by 2. So for both the cases, you see, right, whether you send 0 or 1, right, mean changes. For the 0, it is minus root EB. For 1, it is plus root EB. But the variance remains same. Okay, so the variance value is calculated as n naught by 2. Okay, so that, this is n naught by 2. So that is equal to sigma square equal to n naught by 2. So we got all the values we needed. We need to substitute in the PDF, right? So this implies the PDF which we are going to write of the x1 when the symbol 1 was sent. What's the notation? If you remember, this is fx1 of x1. After this slash, you write 1, right? So this has to be, we should write the standard Gaussian function. So the standard Gaussian function is 1 divided by the root of 2 pi sigma square into the exponential of minus of x1 minus mean the whole square divided by 2 sigma square. Substitute the values which we have calculated just now to get the final answer, right? So that should be equal to, I have to substitute mu equal to root EB and sigma square equal to n naught by 2, right? So the similar calculation we did already, right? So this should become easy for us to run. So this is equal to, so I can write 1 divided by, see the 2 and the n naught by 2, that will get cancelled.